Welcome to the third lecture from my thermodynamics course. In this video, we're first going to be going over processes and cycles. So to begin, let's go ahead and look at the definition of a process. A thermodynamic process is basically any change that a system undergoes from one equilibrium state to another. So change that a system undergoes from one equilibrium state to another. And now thermodynamic processes do tend to involve a path, which in this case is simply a series of states through which a system passes during a process. So a number of states through which a system passes in a process. And now here we must note that the initial and final states of a process, the path followed during that process, and the interactions with the environment should all be specified in order to fully describe a process. So to completely describe a process, we need the initial and final states of a process, the path followed, as well as any interactions with the environment. So once again, we need four main things: both initial and final states, path followed, and interactions with the environment. So just be sure to keep this in mind for future reference. And now just to help further visualize a path, let's say we have two properties A and B on the x and y axes of a graph. And somewhere here on the bottom left we have state 1, and on the top right we have state 2. For this process to go from state 1 to state 2, of course, it's going to need to follow a path, which is represented here by this green curve that connects state 1 to state 2. And so assuming that we know the interactions with the environment, since this graph includes state 1 and state 2, as well as the path, this is basically a graph of a process. Now we'll go ahead and focus on a specific type of process known as quasi-equilibrium or a quasi-static process. Fundamentally, this is basically a process that occurs in such a condition that the system remains infinitesimally close to an equilibrium state at all times. So again, system remains infinitesimally close to an equilibrium state at all times. And along with this, a key thing to note is that this is typically a sufficiently slow process that allows a system to pretty much adjust itself internally so that its properties in one part do not change any faster than the other parts. So again, a process that is sufficiently slow enough to allow the system to adjust itself internally so that properties in one part do not change faster than others, or in other words, to allow the system to internally remain in physical thermodynamic equilibrium, which is another key thing to note here. The system remains in internal equilibrium. And also the system's properties such as pressure and temperature are well defined. So properties like pressure and temperature should be well defined. So now, for example, let's say we have a slow compression process, keyword slow. This is typically known to be a quasi-equilibrium process because it is a slow process. Now for this slow compression process, let's say it involves a cylinder and a piston as shown. Let's say this dotted piston here is the initial state, and then this solid piston on the left is a second state, where the piston is of course being pushed to the left, compressing air that is inside the cylinder. Now this type of configuration here is known as a piston cylinder device, which is fortunately an intuitive name that is quite easy to remember. And of course here, this is the piston and the outside is the cylinder. And now based on our knowledge of quasi-static processes, In this type of process, there's basically more sufficient time for molecules to redistribute, so in a sense, they remain more uniform. Hence, this is part of the reason why the system is said to remain in physical internal equilibrium. And now, in contrast, let's say we have a fast compression process, which consequently is known as non-quasi-equilibrium. Here we will also use a similar piston cylinder device, but except the piston moves significantly faster than the one before. So as a result, the second state of the piston is further to the left than the slow compression. And now in consequence, here there is basically less time for molecules to escape, pretty much causing them to pile up and of course increasing the pressure of the system in return. So again, less time for molecules to distribute or escape, causing dramatically higher pressure. And well, of course, physically this happens when there is a pileup of molecules in an enclosed area. And now we can also represent a compression process using a pressure versus volume graph, where for instance we have state 1 on the lower right and state 2 on the top left, and the process follows the path from 1 to 2. And so on the horizontal we have volume 1 and volume 2, where you can of course see the decrease in volume. And this graph is usually simply known as a PV graph, which again is pressure versus volume. And so here we can also see that pressure and volume are inversely proportional, since pressure increases as volume decreases. Where of course on the graph you can see that V2 is less than V1, and then in pressure, P1 is down here, P2 up here, and P2 is greater than P1. Next, we'll go ahead and look at different types of processes, which we'll commonly see in thermodynamics. So first off, we have a process that is known as an isothermal process, which is basically a process in which temperature T remains constant. And this is of course temperature throughout a system. So the main thing to remember is that the temperature of a system remains constant. So that is an isothermal process. Next, we have another process which is called an isobaric process. And this is a process where pressure P remains constant. So this time it's pressure that remains constant. And likewise, this refers to the pressure of a system. So that is an isobaric process. And lastly here we have an isochoric process. And this is a process where specific volume V remains constant. So an isochoric process involves constant specific volume. So these are the three major processes that are used to uniquely describe a thermodynamic process. And now usually these processes tend to involve some kind of cycle. And while in thermodynamics, a cycle typically occurs whenever a system returns to its initial state at the end of a process. So this is of course just like any other cycle which we see anywhere else in the world, where something eventually returns to its start or its fundamental state at the end of its process. And now to briefly help visualize a cycle, we can of course graph a cycle by simply adding two different states and then drawing in the process path that goes from the first state to the second and then back to the first, just like so. And so of course this circle that we end up with essentially represents the cycle. So basically keep in mind that final equals initial. And so I guess a slightly more accurate depiction of this on the graph would be, say we actually have a total of 5 states. So 2 will now be somewhere here, then 3, 4, and then 5. The final state is equal to 1. So this goes from 1 to 2, and then 2 to 3, 3 to 4, and then 4 to 5. So of course, the initial state 1 equals final state 5. So hopefully this intuitively shows you how a cycle returns to its initial state. Moving on, we'll look at a few terms that are commonly used to describe different thermodynamic processes. First, we have the term steady, which basically means no change with time. So a steady process fundamentally has no change in its properties over time. Next, we have the term transient, which basically describes a process that does involve change with time. So essentially, it's the opposite of steady. So these types of processes, of course, do involve shifts in the values of a system's properties over time. Another kind of term used to describe a process is uniform, which basically means that, note carefully here, there is no change with location over a specified region. So again, there is no change in the values of a system's properties with location over a specified region. And last but not least, we have something known as a steady flow device. And so a steady flow device is basically a device that operates for a long period of time under the same conditions. So again, these are devices that operate for long periods of time under the same conditions. And so these are four major terms to keep in mind of moving forward, as these will help you properly analyze systems which we'll encounter in future practice problems. And now one last thing to note here is that each of these can be represented by partly idealized processes. And now, more specifically, we'll go over a steady flow process. And so, as the name suggests, a steady flow process is one that typically involves a fluid that steadily flows through a control volume. So, it's a process during which a fluid flows through a control volume steadily, hence the name steady flow. And now a key thing to keep in mind here is that fluid properties in a steady flow process may change from point to point, but they remain the same or constant at any fixed point during the process. So again, fluid properties can change from point to point, but they remain the same at any fixed point throughout the process. So now, for example, as referenced in the book, let's say we have a control volume here represented by this rectangle where we have mass going in on the left side and mass going out on the right side. Then we have different temperatures that vary in each corner of the control volume, just like so. And now let's say that this represents the control volume at two different times, T1 and T2. And now let's say that this system is supposed to represent a steady flow process. Each of these temperatures are of course located at different positions. And so we can say that the temperature varies at different positions. And now again, since this is the system at two different times, we can conclude that the temperature, a property, varies with position, but not with time. Again, because each of these individual temperatures are the same at T1 and T2, regardless of their change with position. So, for instance, we can say that temperatures are equal at, for example, 1 p.m. and 3 p.m. if we wanted to add specific times. So again, this describes a steady flow process where a system's properties do not change over time. And now, just to make this a bit more clear, I went in and copied the previous diagram onto here and basically copied it over again to show the system at the two different states or times, one being at 1 p.m. and the other at 3 p.m., where we can more easily see that the temperatures remain constant over time, while they vary with position inside the control volume. So hopefully this gives you a helpful depiction of a steady flow process. Now another important thing to remember is that volume, mass, and total energy E of a control volume remain constant during steady flow. So again, volume, mass, and total energy remain constant, which is a key assumption for steady flow processes. And so to note this down mathematically, we can say that the mass of a control volume, mCv, is constant, which essentially implies that the initial mass m1 is equal to the final mass m2. And of course, this can be the mass of a fluid flowing through a control volume. And similarly, we can say that capital E CV, which in this case is the total energy of the control volume, is constant, where the initial energy E1 equals the final energy E2. And so this is a fundamental concept or assumption that you should remember, which is key to solving and analyzing steady flow systems, as this fundamental principle is used for mass and energy balance. Next, let's go ahead and look at a few common devices that are used for continuous operation, which are devices that are typically used in thermal power plants. Now, one of these devices are turbines, which are, of course, very iconic in industry, as they have various applications, such as from power plants to airplanes. And essentially, turbines are used to basically convert kinetic energy, usually from a fast moving fluid that flows through the turbine, into mechanical energy in order to spin a motor that generates electricity and or to simply output work. Next, we have pumps, which are also widely used in a variety of applications. And now pumps are typically used for basically moving a fluid from one point to another. And this is done by applying work energy, typically from electricity. Next up, we have boilers, which you could say are typically the core of a power plant. And now in power plants, the main purpose of a boiler is to generate steam from water that runs through a coil inside the boiler by heating up the water from a heat source via heat transfer. So it is basically a heat exchanger, and the heat is usually produced from burning a fuel such as coal, oil, or natural gas. Moving on, we have condensers, which are another type of heat exchanger, but in reverse of boilers. So instead of heating up the water, the goal is to cool down the water. And this is also achieved through heat transfer, this time transferring heat from the hot water to a cool medium such as a refrigerant or the surroundings. And lastly, we have heat exchangers in general, which again are devices that exchange heat between a hot and a cold medium through heat transfer, such as boilers and condensers. So these are again devices for continuous operation, which you will encounter throughout your study of thermodynamics for engineering. And now just to finish up this lesson, we'll briefly go over a little bit more about temperature, as well as the Zeroth Law of Thermodynamics. So a key thing to know about temperature is that several properties of materials tend to change with temperature in a repeatable and predictable manner. And so, for example, mercury thermometers are based on the expansion of mercury with temperature, which is of course how we are able to read conventional thermometers. Next, as previously discussed, you should also remember that when a body is brought in contact with another body that's at a different temperature, heat will transfer from the body at higher temperature to the one at lower temperature until both bodies have reached an equivalent temperature, which is of course thermal equilibrium. So these are a few crucial concepts to keep in mind about temperature. And once again, remember that heat always flows from a region of high temperature / energy to a region of low temperature / energy. Now the last principle which we'll cover for today is known as the Zeroth Law of Thermodynamics. And now this law definitely does have a bit of an odd name, so you might be wondering what exactly it means. And while this law basically states that when two bodies are in thermal equilibrium with a third body, then they must also be in thermal equilibrium with each other. So essentially, three bodies will end up being in thermal equilibrium with one another. And of course, you might be thinking that this sounds very obvious, and that is true, but this law is supplementary to the first and second laws because this can generally not be inferred from neither the first or second law. And according to the reference thermodynamics book, this law was first formulated by the physicist Ralph H. Fowler in 1931. And also the reason why they called it the Zeroth Law is because it was actually recognized after the first and second laws, and it is pretty much meant to come before the first and second laws. Hence the Zeroth Law. And now this law also primarily serves as a validity for temperature measurements. So basically it validates any temperature measurement that results from a thermometer. And now just to help better understand this law visually, let's say we have three different bodies, A, B, and C. And for instance, we know that A and C and A and B are each in thermal equilibrium. Then the Zeroth Law will tell us that B and C are also in thermal equilibrium. And so in this case, we can say that A is that third body. And now just to relate this to the validity for temperature measurements, here we can say that this third body is a thermometer, which is of course used for measuring temperature. So to conclude, the Zeroth Law would basically imply that the thermometer is in thermal equilibrium with the system.